In previous two videos, we have studied Sylow first theorem and second theorem concerning finite group G of order p raised to power n q. In the present video, we will study Sylow third theorem and its uses in determining normal subgroup of a finite group. Let G be a finite group of order p raised to power n q, where p is a prime, q is a positive integer, such that p doesn't divide q and integer n is non-negative. So it is easy to see that p raised to power n divide order of G, but p raised to power n plus 1 doesn't divide order of G, because if it will divide, then p will divide q. So this condition implies that p n plus 1 doesn't divide order of G. By Sylow first theorem, as we have studied in our first video on Sylow theorem, G has a subgroup of order p raised to power n. And we know that the converse of Lagrange's theorem is not true in general. However, it partially holds, as we have seen in Sylow first theorem. If a prime power divides order of G, then there exists a subgroup of that order. The largest prime power order subgroup exists in G. So this subgroup, the largest possible prime power order, is known as Sylow P subgroup. So this is given in this Sylow first theorem. If G is a finite group of order p raised to power n q with the conditions given above, then G has a subgroup of order p raised to power n. So Sylow third theorem gives existence of a subgroup of order prime power that divides order of G. So we see that in Sylow second theorem, if there is a subgroup of order prime power, then there may be more subgroup of that order, but in Sylow second theorem it is stated that all Sylow P subgroup of G are conjugate, means that if there are finite number of Sylow P subgroups of order p raised to power n, then they all will be conjugate and hence they will be isomorphic. The main object of this video is to study Sylow third theorem and present its proof in very simple way. This techniques will depend upon double cosets. So before giving proof of Sylow third theorem, we give some auxiliary results. So first we came to know that this theorem, Sylow third theorem, okay, and it's a simple corollary. This is appears for uniqueness of a Sylow P subgroup. So if for any prime P there are finite many Sylow P subgroups, as we are considering finite group, so let NP denotes the number of Sylow P subgroup of G. Then according to Sylow third theorem, we see that NP will leave remainder 1 when divided by P and NP will divide Q. So this useful information helps to characterize normal subgroups and number of Sylow subgroups of a finite group G. And we know that the study of normal subgroup very much belongs to the study of simple groups. So we will see that the Sylow third theorem gives very interesting outcomes to determine simple groups. So another situation, we can write NP as the number of Sylow P subgroups of a group is of the form pk plus 1. So the number of Sylow P subgroup of the type pk plus 1, where k can be determined by using this condition 4k plus 1 divides q. So From here we can determine k. If k is 0 here, then you will find there is only one Sylow P subgroup and there is only one Sylow P subgroup. It means that it will coincide its normalizer and hence it is a normal subgroup. So as we have discussed in proving Sylow third theorem, we need some auxiliary result. First one is this: let P be a Sylow P subgroup. Then the number of Sylow P subgroups of G is equal to the index of NP, normalizer of P in G. So by Sylow second theorem, we know that all Sylow P subgroup are conjugate. Let C be a collection of all conjugate subgroup of a Sylow P subgroup P. Then C contains NP distinct elements. Normalizer of P is the collection of element G for which P is invariant in G. So NP is a collection, X belongs to G such that XP, X inverse equal P. Note that we are taking left conjugate of subgroups P. One can take right conjugate, but in throughout this study we will take left conjugate. It is well known that NP is a normal subgroup of G containing P. Let index of NP in G is K. It means that NP has K distinct right coset in G, and therefore G can be written as union of these left cosets. Because we are taking left conjugate, so here left conjugate, so throughout this study we will take left cosets. If you take right conjugates, means X inverse Px, then we can make use of right cosets. So students should note this point. So there are K distinct left cosets of NP in G like this, and we know that G can be covered by these left cosets. Let X be a collection of all conjugate of P. Obviously X is a subset of C because C contains all conjugate of P. Now we will show that C is also contained in X. For this we will take any arbitrary element of C and we will show it will be in X. So take C belongs to C, T belongs to C, be any element. Since T will be a conjugate subgroup of P, so there exists X belongs to G such that T equal XP X inverse. Since G is a union of right left cosets of NP in G, so X will belongs to G, and therefore as we can see here X belongs to G, so X belongs to this union, and therefore X belongs to some left cosets of normalizer of P. So we can see here, so there exists a unique integer J such that X belongs to Xj NP, means that X belongs to this left cosets. X belongs to this left coset, it means that X can be written as Xjy for some Y belongs to NP, and with this notation we see that T can be expressed as we have taken here XP X inverse. Now on substituting X by Xjy we have this expression, and applying elementary results of group theory you see that this can be written as Y inverse Xj inverse, and after associativity you can use to write Xj Y P Y inverse Xj inverse. Now since Y belongs to NP, so Y P Y inverse equal P, so it is P here, So we see that T was arbitrary element of C and it is again of the type, it means that T belongs to X, and showing that T belongs to X, and it follows that C is nothing but X. So C all conjugate of P can be expressed in such a way. It means that the collection of left cosets of normalizer of P completely determine all conjugate subgroups of P. Since cosets of NP are distinct, so it is not a big issue to prove that these Sylow P subgroups containing X are distinct. So all Sylow P subgroup can be taken in X, and these are K, and we have already discussed that there are total number of Sylow P subgroup is NP, so NP equal K. So in this way we proved the result. The number of Sylow P subgroups in a group G is equal to the index of normalizer of P in G. This is an example when we are considering symmetric group of degree 3 having 6 element, then it will have 2 Sylow subgroups and 3 Sylow subgroups, Sylow 2 subgroups and Sylow 3 subgroups, as 2 and 3 are primes dividing 6. If we take P is a subgroup of G having these 2 element, a Sylow 2 subgroup. So if you take normalizer of this, obviously it is equal to P. So normalizer of this P is P. So you can, and it is equal to G, in fact you can say. So number of Sylow P subgroup, number of Sylow 2 subgroup is order of G upon order of NP. So order of NP is, because NP is P here, so this is 2, so order of G is 6 by 2 is 3. Similarly, if you take P is this Sylow 3 subgroup, then because this is a normal subgroup of G, so NP will be G, and in this case it is a Sylow 3 subgroup is 1 here, number of Sylow 3 subgroup is 1. So it is a simple example. Now we will give proof of Sylow third theorem. Let P be a Sylow P subgroup of order P raised to power n. So for any G belongs to G, we can take a subset of G containing such element A, G, A inverse, A belongs to P. So this is a subset of G. So as we have studied in our previous video related to Sylow second theorem, we have discussed such type of subset H, A, K, and it is a particular case of that problem. So we are considering H and K both equal to P here. So in that video we studied there is a equivalence relation, and these will be equivalence classes of that equivalence relation. So this is a subset as a equivalence class, okay, and G can be written as union of these classes, disjoint classes, and therefore order of G is sum of number of elements of these classes. So this sum of number of these classes vary over G. G belongs to G. Now there may be situation when G belongs to NP and G does not belongs to NP. So students should note this point that G is a finite group and PGP is a subset of G, forms a partition for G. Therefore G is covered by disjoint classes of disjoint subsets of these subsets, and therefore order of G can be written as the sum of number of elements of these subsets. Now these subsets varies over the summation varies over elements of G, so this element can be taken in two ways: G belongs to NP or G does not belongs to NP. So this summation can be further written in this form. Now we will determine the number of element here and number of element here. So to determine this first summation, G belongs to NP, we take G belongs to NP, then PGP can be written as GPGP. So because GP can be written as this way, associativity we can use here. This is a just an action form of elements. So GP is a cosets, and we are taking action of elements of P in left side, and if we consider this action, then this action is equivalent to this action. Okay, so because GP is same as PG, because G belongs to NP, G belongs to NP, so GP equal PG. So if you apply this action on elements of P, because P is a subgroup, then that will be action, this is same equal to PG, because this is a P is contained in PG, and with respect to identity E you can write in this way, and therefore this can be written as PG, and PG because G belongs to NP. Okay, then and P is a subset of NP, so PG is a subset of NP. So finally, when G belongs to NP, student can see PGP is contained in NP. PGP, this set is contained in NP. So it follows that NP, as we know that P is a subgroup of NP, and therefore NP can be written as a disjoint union of the right cosets of P with respect to element of NP, and this PG is same as PGP, as we have seen here, PGP. So the number of order of NP is sum of elements of PGP. Okay, so in this way we obtained this first summation, in which we find that this is order of NP. On the second summation, we take G doesn't belongs to NP. In order to determine the number of element in PGP in this situation, we note that P intersection GPG inverse is a proper subgroup of P. If one take this is not a proper subgroup of P, then it will be P, and it will be P in this situation GPG inverse equal P, and hence G belongs to NP, which is a contradiction. So it is very easy to note that P intersection GPG inverse is a proper subgroup of P, and P is a Sylow P subgroup, and its order is P raised to power n. So the order of this subgroup is also prime power, P raised to power r, and it is a proper subgroup. P intersection GPG inverse is a proper subgroup of P, so it will be a proper divisor. It will be a number which is lesser than that order of G, order of P. So R will be here less than n, R will be here less than n, and therefore this also we have discussed in previous video, order of HAK, where H and K both are P. So this is a double coset. Number of element in double coset is equal to number of element in P into number of element in P divided by number of element in this subgroup. So this is P raised to power n, P raised to power n, this is P raised to power 2n, and this is P raised to power r. So the number of element in PGP is P raised to power 2n minus r, and here r is less than n. Now from this expression order of G here, and this is order of NP, and this is P raised to power n 2n minus r. So from expression 1 we obtained this. Okay, we obtained this. Since P is a subgroup of NP, so P divides order of NP, but P raised to power n is the largest power that divide order of G, and NP is a subgroup of G also. So it means that order of NP will be P raised to power n into S, and where S will divides, S will be a divisor of Q here, and P will not divide S. Otherwise P raised to power n plus 1 divides order of NP, which is not possible for group any divisor of group G, because P raised to power n plus 1 doesn't divide order of G. So student, in this expression we are having order of G is order of NP plus summation of this, and we observe that order of NP is P raised to power ns. So if you divide throughout this expression order of NP, then we have this order of G upon order of NP. We divide, actually number of Sylow P subgroup is index of NP in G, and it is equal to order of G upon order of NP. And if you take here this is order of G, substitute here, then that will be 1. When we divide this by order of NP, this will be 1, and this will be order of NP, and order of NP is PNS. So you take here Pn minus R divided by S, and this summation has finite number of, this is a finite sum, so finite sum, so there will be finite number of elements in NP which does not belongs to G. So let D be such elements. So if you take, there are D such elements varies over this summation, then this summation can be written as D into PNR divided by S from here. So one can note that this is the number of Sylow P subgroup, it is order of G upon order of NP, and from this expression we will get 1 plus summation G does not belongs to NP, P raised to power 2n minus R, PNS, and Pn divide here, this is Pn minus Rs. And if we take, there are D distinct such elements, so this expression can be written as. So now you see that left hand side is NP, and it is an integer, and 1 is also integer, so this expression will be integer. So this expression will be integer since P doesn't divide S, so it means that S will divide D. S will divides D, where D is the number of double cosets of the type this, as we have discussed. So NP is an integer, so S divides D, hence that number will be multiple of P. When S divide D and N is greater than R, so this number is a multiple of P. So this number is a multiple of P, so we can write it Kp. For some integer K, we can this. So in this way we proved that NP is 1 plus Kp. Okay, NP is 1 plus Kp, and it was our required result. Now in this example we take a group of order 45, and it has Sylow 3 subgroup and Sylow 5 subgroup. So Sylow 3 subgroups of order 9 and Sylow 5 subgroup of order 5, and the number of Sylow 3 subgroup N3 is of the type 3k plus 1 by the previous theorem, and 3k plus 1 will divides 5. When 3k plus 1 divides 5, here 3k plus 1 divides 5, then only possibility is for k is 0. So k is 0, so n3 is 1. So n3 is 1, it means that there is a normal subgroup of order 9. So G has a normal subgroup of order 9. In same way, we see that n5 is of the type 5l plus 1, and 5l plus 1 divide 3, and the only possibility for L is here 0. So n5 is 1 here, and therefore there is only one Sylow 5 subgroup, and hence it is normal. So G has two subgroups, normal subgroup of order 9 and order 5. We can say H of order 9 and K of order 5. We know that any group of order P square is abelian. So H is abelian and K is a cyclic group of prime order. So, and one can see that in such situation, because H intersection K is identity, so G can be written as a direct sum of these two subgroups, and they are at most abelian, and therefore G is an abelian group of order 45 here. This is another example in which we will show that a group of order 48 has a normal subgroup, non-trivial normal subgroup, and therefore a group which has a non-trivial normal subgroup, a normal subgroup other than identity and itself, is called simple group. So a group is said to be simple if it has no normal subgroup other than identity and itself. So we will show that a group of order 48 is not simple here. So if you take here 48 can be written as prime decomposition 2 raised to power 4 into 3, and there are two Sylow subgroup and Sylow 2 subgroup and Sylow 3 subgroups. Sylow 2 subgroup will be of order 16, and the number of Sylow 2 subgroup will be of the type 2k plus 1, 2k plus 1 divide 48, and since 2 is coprime with 16, 2k plus 1 is coprime with 16, so 2k plus 1 divide 3, and when 2k plus 1 divide 3, then k can be taken as 0 or 1. So number of Sylow 2 subgroup will be either 1 or 3. So if it is 1, number of Sylow 2 subgroup is 1, then it is normal subgroup, and hence we have a normal subgroup of order 16. In case of when number of Sylow 2 subgroup is 3, so there will be, we can assign S1, S2, S3. These are 3 Sylow subgroups of order 16. So if we take intersection of these two subgroup S1 and S2, then it is a subgroup of S1 as well as S2. Let order of S1 intersection S2 is T. So the because order of subgroup divide order of group, so order of T can be written as 1, 2, 3, 4, 8, and it cannot be 16. T choice of T cannot be 16, because if it is 16, then S1 will be identical to S2. So since S1 is not identical to S2, so T cannot be taken as 16 here. When T is a 16 here, so the number of element in S1, S2, this may not be a subgroup, but this is a subset of G, and it has element order of S1, order of S2, and this is 256 upon T, and therefore this number can be taken as, so because S1, S2 is a subset, so it can not have 256 element, 128 element and 64 element. So the possible choice, only possibility of elements of S1, S2 is 32 element, and therefore T will be 8 here, corresponding to these 32, T is 8 here. So order of S1 intersection S2 is 8 here. Since it S1 intersection S2 has a index 2 in S1 S2, so S1 intersection S2 is a normal subgroup of S1 and S2, and then we know that S1 S2 are contained in this, because this is the largest subgroup in which S1 S2 is normal, S1 intersection S2 is normal. So S1 S2 intersection is normal in S1 S2 as well. So S1 S2 will contain in n intersection and S1 intersection S2. So this point should be noted here, why we have such situation. Now S1 S2 is contained in this, so their product will also contain in it, and therefore order of normalizer of S1 intersection S2 will be greater than equal to 32, and the only possibility for this is as a subgroup is G. So it means that S1 intersection S2 is a normal subgroup, and it proves G is a simple group. So these are some applications which can be seen by the students. I hope student will try to solve these applications. Thank you.